Hi, today I'll be talking to you about the DataJoint element for multiphoton laser scanning calcium imaging analysis with data acquired with the scan image or scan box or Nikon NIS acquisition system and processed with either Sweet2P or Kaiman. Before we jump into this pipeline, I will draw your attention to the elements.datajoint.org webpage, which is our main webpage that goes over the DataJoint Elements projects, which is a NIH-funded initiative for data workflows for neurophysiology. And all of our workflows and DataJoint elements are hosted on GitHub. So here we have the DataJoint workflow for calcium imaging, and we have the accompanying element calcium imaging as well. And this DataJoint workflow for calcium imaging comprises of 4 different elements: element lab, animal, session, and calcium imaging. And the pipeline is shown here with the upstream elements, subject, session, and equipment, as well as the calcium imaging element overall, which can process your Sweet2P and Kaiman data here in these middle tables, and then store data for your motion corrected results and segmented mass and fluorescence traces and deconvolved neuronal activity traces as well. So I will switch over to my integrated development environment, Visual Studio Code, that I'll be using. Please refer to our previous videos on YouTube, on the DataJoint channel, on how to set up your DataJoint workflow to run your analysis. And I will, before I dive into this notebook, I'll draw your attention to the data that we'll be referring to. So that's shown here on the right under a directory called test data. We have subject 3, and then the session directory, which is this set of numbers here, 210, 107, run 00, and so on. And within this directory, we have the scan box acquired data, so this SBX file, as well as the Sweet2P directory, which stores the Sweet2P results, planes 0 through 3. So this data was already processed through Sweet2P, so we'll be loading this into the DataJoint element and the database. But alternatively, this data could be, the raw data could be analyzed with Sweet2P within the DataJoint element. So in the first set of cells, I import the relevant packages, and this first cell specifically, I'm changing directories to my workflow directory, which if I scroll down here on the right, it stores the DJ local config JSON file, which has the credentials for the database that I'll be connecting to. Next, I'll be importing all the relevant modules from the pipeline script, which if I go to this pipeline script, this is the script that sets up my pipeline. So it imports the relevant modules at the top, and then it activates these data elements, so the lab, subject, and session, as well as the imaging element, the element calcium imaging. So what that does is it instantiates a version of these tables on the database. So if I go back to my Jupyter notebook, so what I'm doing here in cell number 2 is importing all of those modules from the pipeline script into this namespace. And then I'm plotting a DJ diagram. So what you can see here, if you start at the top, you have your subject table, your session table, and then your scan table. And that stores all metadata about your experimental session that's been acquired and that will be processed. And your scan info table is what reads in the scan box or scan image file and stores data about the specific acquired file. So the number of fields, the channels, and so on. And then the next set of tables is the processing task table, which what's not shown here is the param set table, which stores the parameter sets. And then for a given scan and a given set of parameter sets, you can declare a processing task entry, which then in the processing table will be run. So either you could run a set of parameters for Kaiman or Sweet2P within this table. And then below this table which are not shown here, are all the tables to store your data into the motion correction and segmentation tables, which we'll be going into more detail later on. So looking at the heading of the subject table, this stores the subject as the primary attribute, and then the secondary attributes are the gender, birth date, and description. So we'll be inserting one entry into the subject table, subject 3 for this example, with the gender, birth date, and description. We'll be entering in data into the lab.equipment table. So we'll be saying the scanner is scan box. And then the session table stores the subject and session date time as primary keys, and there's no secondary attributes here. So we'll be creating a session key, which is just a dictionary of the subject and session date time. And we'll be inserting that entry into the session table using the insert one method. And if we print the contents of the session table, we can see that the entry was inserted correctly. And then we'll be entering into the session directory table. So the session directory table has a foreign key reference to the session table, and the secondary attribute is a session directory. So we'll be making an insert into this table for the subject, session date time, and then the session directory. So it's a relative directory, subject 3, and then this varchar subdirectory. And we can see, if we print the contents of the session directory, that the data was inserted correctly. Then next, we'll be entering into the scan manual table. So subject, session date time, scan ID are all the primary attributes. The scanner, acquisition software, and scan notes are the secondary attributes. And so we're entering in an entry for this scan. So scan 0 is an example, and the scanner is scan box, and the acquisition software scan box. So then next in the scan info table, this will look at your session directory, load all the scan box files, and enter in the number of fields, channels, number of frames, frame rate, and so on. We'll define a dictionary called populate settings, which has display progress equals to true. So then when we run the populate method on this scan info imported table, we'll pass in those populate settings, which tells this populate method to display the progress of its run. So that's what you see down here. There was only one key to populate, but it shows the progress. And then we can print the contents of scan info. And we can see here that this scan 0 for this session date time, had 4 fields, 1 channel, 7,500 frames, and so on. Then next we can define some parameters. So some default parameters from Suite2P. And we'll make an entry with those parameters into the processing param set table using the insert new params helper function, which ensures that you don't enter in duplicate sets of parameters into the same table with a different processing or a different param set ID. So we'll say the processing method is Suite2P. The param set ID in this case is 0. We'll enter in the parameters and the description as well. So in this case, we're using the default Suite2P parameters. The next table is the processing task table, which defines your scan that you're planning on doing processing with, and then the associated or the parameters that you're planning on processing that scan with. So in this case, we're going to be processing the subject 3, session date time, and scan 0 with param set ID 0. And if we recall from above, that param set was for Suite2P and their default parameters. And the processing output directory is the the same session directory with the Suite2P subdirectory. And what's not shown here is the task mode is actually, as a default, set to load. So what this is saying is load in the data that's stored within the Suite2P directory. Alternatively, we could set the task mode equals to trigger. In that case, if the Suite2P directory is empty, what this will do is run this parameter set on this raw acquired image for Suite2P and save the results within this directory. And that the actual running occurs within this processing table. So it's a computed table. So you'll use the populate method, and it'll either, with task mode load, it'll either check that the data is accurate or check that the data exists on disk. Or if it was trigger, if task mode was equal to trigger, then it would actually run Suite2P or Kaiman within this step here. The curation table allows a user to manually curate their results outside of the element and specify that here within this table. In this case, we've set the manual curation. We've specified that we are actually not curating our results. So we set a curation ID equal to 0, an arbitrary curation time. The curation output directory is the same directory where our process results were, Suite2P. And again, we are not manually curating our results in this case. The motion correction table is an imported table. So you run the populate method on this table, and it will load in all the data from your Suite2P results for your motion correction shifts, as well as the summary images. Next, we have the segmentation table, which is another imported table and will load in your segmentation mass for your Suite2P analysis. And next, you have your fluorescence table, which will load in for each mask the fluorescence traces. And lastly, we have the imaging.activate table, which loads in the deconvolved neuronal activity for those fluorescence traces. So in summary, this video in this notebook shows you how to ingest data into a DataJoint element for calcium imaging and thereby into a database. And in the next set of videos, we'll be showing you how to query, fetch, and plot that data that has been imported into the database.